Now, making sense of our solution, we should have units of EMF or voltage here, which is joules per coulomb. Okay, well, unit of A is meters, unit of V is meters per second, unit of Y or A is meters. So we have units of meters squared here, units of meters squared here, units of meters per second here. The meter squared units here and here go away, and we end up with units of K prime times units of I times units of V. Okay, now what are the units of I? Well, I is in amps, V is in meters per second, K prime is in Tesla, let's get this right, it's Tesla per amp meter. Okay, so I'm sorry, it's Tesla meter per amp, and we can easily figure that out just by writing down the force equals, or the magnetic field equals K prime times I delta L over R squared, and that comes right out. So it's confusing to remember it. You've always got to remember how to go back, but we end up here with units of Tesla meters per amp times amps times meters per second. Now your amps divide out, you end up with Tesla meters squared per second. Now what's a Tesla? Okay, think about that for a second. A Tesla is a Newton meter per amp. So and again, go back to the defining relationship of your magnetic field, and you get this. So that's Tesla meter per amp times meter squared per second. And I've got this meter in the wrong place, just demonstrating for you why you don't want to try to memorize these conversions. You simply have to understand them, and this goes back, we've done this previously. Anyhow, you end up with a Newton meter per amp second. Okay, Newton meter is a joule, an amp is a coulomb per second multiplied by a second, and I need to get this back a little further to get the whole board. Okay, so an amp second is a coulomb. There's your joule per coulomb, which is what we want to get up here. So this whole process, and I've abbreviated the process just for units, just in interest of time and the fact that we've done a lot of it. The units do work out, which is a pretty good indication that we've done something right. Now the other part of this is that we want to see if this makes sense. First place, if we pull the loop away from the x-axis, from the line current, what's going to happen to, first of all, the flux, and second of all, to the rate of change of the flux. Okay? Now, the flux is going to be proportional to natural log of A plus Y over Y. A is fixed. As Y gets large, A plus Y is not going to differ much from Y. So this natural log is going to approach 1, which means that it's going to approach 1 at a decreasing rate, as you can verify by doing some derivatives and so forth. And that implies that the flux is going to change more and more slowly, because we're approaching a constant value here, and this flux is clearly decreasing with increasing Y. And of course, when I say the natural log, the A plus Y over Y approaches 1, meaning the natural log approaches 0. So the flux approaches 0 as Y approaches infinity, and in a way that, at least as you approach infinity, it's an approach at a decreasing rate. So that the derivative of the flux which would be the slope of your flux curve, flux versus distance curve, is going to approach zero. Okay, and of course the derivative will be negative, and that comes right out here. Okay, so we expect the derivative to approach zero as y approaches infinity. And we see that that is indeed the case. The only y's we have are in the denominator. As y gets large, the a becomes unimportant, and we have a reciprocal y squared. So that this EMF that you get is going to fall off at some point. It's going to approach falling off at an inverse square rate. It's going to approach falling off as an inverse square. Okay, if you're close to the current source, then the behavior is somewhat different, because then the y becomes insignificant. The y here becomes insignificant in comparison with the length of the side of the square. So when you're very close, y is a lot smaller than the side of the square. This term is more or less just equal to a. The change of y doesn't have much effect on this factor. Of course, you have a y here. And the result is that the EMF is going to fall off at a rate that's inversely proportional to y. So when you're very close to the loop, the rate is inversely proportional to y. When you're far away, or the EMF is inversely proportional to y. When you're far away, the EMF is inversely proportional to the inverse square of y. Now this entire expression is just proportional to 1 over ay when you're close, when y is close to 0. So here's y on this axis, and here's a graph of 1 over ay. It's going to be just like a reciprocal first power curve. And then you have the graph of 1 over y squared, which is what you get when y is a lot bigger than a, and that's going to be this green curve here. And the two curves cross when y equals a. You can verify that. And then you can attempt to see how this curve kind of blends in to this curve. You're going to have this behavior close. You're going to have this behavior far away. So you're going to get something that maybe kind of looks like this. And that's how your EMF will decrease as you pull the square away from the current running along the x-axis. If we want an actual graph of the EMF versus y, we just multiply the 1 over ay by the 2a squared k prime iv factor that we have here, and the 1 over y squared by the same factor, because it's a factor in both. And I'm ignoring the negative sign because we're being kind of sloppy about that. And this doesn't change the way the graphs look. You can just relabel the vertical axis and change from the graph of these two functions to the graph of this times this, and the graph of this times this.